So hello everyone. In today's session, we are going to see the questions of your ADC and DAC that we have studied through your past two lectures. Okay. So the first question over here is the output of a three-stage Johnson twisted ring counter is fed to a digital to analog converter as shown in the figure below. Assume all states of the counter to be unset initially. That means all the states of this counter are initially 0, 0, 0. The waveform which represents the DA converter output V0. Okay. So basically we have this. So let me solve the question in the next page. So you can see we have this DA counter, this Johnson counter. So first let us draw the Johnson counter. So this is Q2, Q1, Q0. So initially this Johnson counter is reset. So that means what? Initially it is 0, 0, 0. So twisted ring counter, what we know? That basically over here we will have 1, 0, 0. In the next clock pulse, this one will shift over here and this 0 will be what? This will be complemented. In the next clock pulse, it will be 1, 1, 1. In the next clock pulse, once again, this will be 0, 1, 1. In the next clock pulse, 0, 0, 1. And in the last clock pulse, once again, 0, 0, 0. We are reaching the repetitive state. So this counting sequence is being fed to this DA converter, okay, DF converter. So you can see if we assume the step size of from 000 to 001, if it is let us suppose it is 1 volt, then over here what is the V0? So this is 0. From that this is 100, so 4 volt. Sorry, this is 4 volt, this is 6 volt, this is what? This is your 7 volt, this is 3 volt, this is 1 volt, this is once again 0. So if I have to draw, so this looks like from 0 to 4, okay, in the first clock pulse it goes to 4, means okay, even we can draw it from here or else it's okay. So initially it is 0, then at the first clock pulse it goes to 4, then in the second clock pulse it goes to 6, then to 7, then it comes to 3, then to 1, and then again back to 0, and this will keep on repeating. Okay, so now let us see which option is it matching. So you can see directly if you check, so this is not the option, we can eliminate it. This is not even the option because first it is going to 4 and here you can see this is 2, so this is also wrong. So option C is also wrong. Over here you can see this is going to 4, then to 5, then to 7, so option B is also wrong. So only correct option is option A. So answer A, the question for this question is your answer number, option number A. So the next question, what we have, a 4-bit D to A converter is connected to a free running 3-bit up counter as shown in the following figure. Which of the following waveform will be observed at V0? So what will be V0? They are basically asking. Okay. So you can see this is a 3-bit up counter. So if I have to draw Q2, Q1, Q0. So this is a 3-bit up counter. So it will start counting from 000 to 001. So these are the counting sequence of your up counter. Okay, so this is the counting sequence of up counter. Here we have a 4-bit DAC where this D2 is always connected to ground. So D3, D2, D1, D0, where this D2 is always connected to ground, and D3 is connected to Q2, D1 to Q1, D2 to D0. Okay, so this is always connected to ground. So let me write it like this. And this is okay. So we have like this. Now what will be V0? V0 is basically what? It is the output of this DAC. Okay, output of this DAC. So simply over here, whatever is the value, if step size is assumed it is 1 volt, so you can see this is a 4 bit. So V naught over here, it will correspond to 0. This is 1, this is 2, this is 3, this is 8, 9, 10, and this is 11. Okay. So once again, this will go to 0, 0, 0. Up counter will keep on counting, and this counting sequence will follow. So for this, if I draw the output waveform, so you can see initially it is 0. Then at the first clock pulse, it goes to 1. Then at second clock pulse, it goes to 2. Then at third clock pulse, it goes to 3. Then from 3, directly to 8. Then to 9, 10, 11, and once again back to 0. Okay. So this will keep on continuing. So now if you see, which option do you think is matching like this? So only one option. Okay. So here we have two cases. So this is not the case. Option A is wrong, because here you can see it is decreasing. So this is not the case. Even option C is wrong. Option D is also wrong. So this look quite similar to option B. Okay. So option B is the correct answer for this question. Okay. So now what is the answer? Can you guys guess? Look, solve this question. So I will give you 1 minute to think about this. So you can see basically a 2-bit flash analog to digital converter ADC is given below. Okay, so we have one 2-bit flash ADC. So this is one ADC. The input is, it varies from 0 to 3 volt. The expression for the LSB of the output B naught as a Boolean function of x2, x1 and x0. So this is your recent question, IIT means GATE 2016. So how do we solve this question? So it's very simple. Let us assume this point is V1, this point is V2, this point is V3. So what is V1? If I apply voltage divider rule, so that is equal to 3 into 100 divided by 100, 300, 300. So that is 600. So this is 1 by 2 volt. V2 is equal to 3 into 300 divided by 600. So that is 3 by 2 volt. V3 is equal to 3 into 500 by 600. Sorry. So this is 2, 4. Okay. So this is 400, 500 by 600. So this is 5 by 2. Okay. 5 by 2. Fine. So we have all this thing now. Now look over here. Basically, it is said the input varies from 0 to 3 volt. So what can we do now? So look. Since my input can vary from 0 to 3 volt. So here basically we will have x2, x1, x0, which are the output of the respective comparators. Along with that, we will be having the digital equivalent output. So that is B1, B0. So Vin can lie between different ranges. So if Vin is less than half, so what will happen? If Vin is less than half, okay, if it is less than half, so over here this non-inverting terminal, it will be less than inverting, so output of this x naught will be 0. Similarly, input means inverting terminal of this, it is at lower value compared to your, sorry, inverting value means non-inverting value is lesser than non-inverting, so this will be also 0. Over here once again you can see non-inverting is less than inverting because this point is already 5 by 2, so over here also this will be 0. So 0 0 0, and corresponding to 0 0 0, b1 b0 will be 0 0. So next, if V in lies between half and 3 by 2. So if it lies between half and 3 by 2, let us take any value. So let it be 1. Okay. If V in is equal to 1, so here you can see basically this is half. V1 value is, sorry, this is 1. This is also 1. This is also 1. But this value is half. This value is 3 by 2. This value is 5 by 2. So you can see over here non-inverting is greater than inverting, so this will be 1. Here you can see inverting is greater than non-inverting, so 0. Here also inverting greater than non-inverting, so 0. So this will be 0 0 1. So this is 0 1. Okay. Next we have if it lies between 3 by 2 to 5 by 2. So if I take one value, let it be 2. So if I take V in as 2, so this is 2, this is 2, this is 2, this is 5 by 2, this is 3 by 2, this is half. So now you can see over here that non-inverting greater than inverting, so this is 1. Here also non-inverting greater than inverting, so this is 1. Here you can see inverting is greater than non-inverting, so 0. So this is 0 1 1. So corresponding to this we will have 1 1 over here. And last is if V in is greater than 5 by 2. So if V in is greater than 5 by 2, then all the comparators output will be 1 1 1. Sorry, this is 1 0. Okay, this is 1 0. So for this one it will be corresponding to 1 1. Now we have to find this B naught with respect to x2, x1, x naught. So you can see basically if you want to write B naught, so B naught is equal to this. So that is x2 complement x1 complement x naught plus this value. So that is x2, x1, x naught. So take x naught common and this is x1, x naught, x2, or you can write it as x naught x1 xor x2 whole complement. So which option do we see? So option A is your correct answer for this question. Okay. Now the next question we have the number of comparison carried out in a 4-bit flash type A to D converter. So how many number of comparisons are carried out in a 4-bit A to D converter? So look over here. In this question particularly, this was 2-bit. Okay, this was what? This was 2-bit. So in 2-bit A to D flash type converter, how many comparators or comparisons? Number of comparisons carried out. So how many number of comparisons are carried out? You can see 1, 2, 3 and 4. Okay, 4 number of comparisons are carried out. Similarly for 3-bit also we have done. So where is that? Over here. So here also you will get what? You will get 8 comparisons. Okay. So for 4-bit, it will be how many? So for 4-bit, it will be 2 to the power 4 comparisons. So that is 16 comparisons will take place over here. So option A. And total number of comparators, we know what? Total number of comparators. So you can see for 2-bit it is 3. Okay. For 3-bit it was 7. So for 4-bit it will be 2 to the power 4 minus 1. So that is 16 minus 1, that is 15 comparisons. Okay. So 15 is the correct answer for this question. So the next question we have, the minimum number of comparators required to build an 8-bit flash ADC is very simple. So total number of comparators just now we saw is equal to what? It is equal to 2 to the power n minus 1. So 2 to the power 8 minus 1, which is equal to 256 minus 1 or 255. So 255 is the correct answer. Now total number of resistor, how many it will be? So total number of resistors is 2 to the power 8. So that is 256. Okay. Look over here. So this is 2-bit. How many resistors we have? 1, 2, 3, 4. So that is 2 square. Similarly, even for your 3-bit, you can see 1, 2, 3, 4, 5, 6, 7, 8. So that is 2 cube. Okay. So over here we have 2 to the power 3. That is your 8. Okay. So next question over here, this is a very good question. An 8-bit successive approximation analog to digital converter has a full-scale reading of 2.55 volt and its conversion time for an analog input of 1 volt is 20 microsecond. The conversion time for a 2 volt input will be. So you need to read the question carefully and then solve. Because such kind of questions, see what happens in your IIT especially, they give questions very much from the basics. So if you have studied the basics very good, then only you will be able to solve such kind of questions, or else you will be just wasting time finding out the wrong answer. So read this question properly once and see if you can get the answer or not by pausing the video. Okay. So what you can see, basically the question is an 8-bit successive approximation analog to digital converter has a full scale reading of 2.55 volt and its conversion time for an analog input is 1 volt is 20 microsecond. The conversion time of 2 volt input will be. So conversion time for successive approximation type, it is equal to how much? It is equal to NTC. Okay, NTC. And this is basically independent of the what? It is basically independent with the value of the input. It is independent. So here you can see if 1 volt is producing, means 1 volt takes 20 microsecond, then obviously the conversion time for 2 volt will be also 20 microsecond only, because conversion time is what? It is independent of your input. Okay. So the correct answer for this question is 20 microseconds. So you can see, if you know the concept, you can solve the question well within like 2 seconds. If you don't know the concept, it will, you might be doing what? You might be calculating the step size like this. Okay, so step size, so that will be equal to full scale divided by total number of steps. So this is 8-bit. So 2 to the power 8 minus 1. So this is 2.55 divided by 255. So that will be 10 microvolt. Now what you might do? Okay, so for 1 volt it is 20 microseconds. So you will now see what is the input bit for 1 volt. So you might be very tempted to do like this: 1 divided by 10 millivolt. So this is 100. So now you might find the binary for 100, and then you might find the binary for this also, and then calculate the conversion time. But that is totally wrong. That is not required. Okay, it's not required. So the answer for this question is what? It is directly 20 microsecond. So the next question is, consider a 4-bit D to A converter, digital to analog converter. The analog value corresponding to a digital signal of 000 and 001 are 0 volt and 0.625. So for 000 is 0 volt, and for 0001 it is 0.0625 volt. Fine. So what is basically told us over here? So basically the step size is told to us. Okay, step size is told to us. It is what? It is equal to 0.0, or you can even say 62.5 millivolt. Okay, the analog value in volt corresponding to the digital signal 1111. So if 001 is this, so this is basically decimal 0, this is decimal 1. Okay, so if decimal 1 is this, then 1111 is basically what? It is decimal 15. So the voltage for decimal 15, it will be what? 15 into 0.0625. So if we solve this, so this is 10,000, and this is 25, this is 5 2000. Okay, so once again 5 fives are, this is 400, and this is your 80. Okay, so this is 3, this is 16, so I have to use the calculator over here. So 3 by 16 is, it is 0.1875. Okay, or else let me check once. 15 into 0.0625. Okay, so I have made some mistake somewhere. So this basically comes out to be what? V naught is equal to 15 into 0.062. Okay, 0.0625. So this comes out to be 0.9375, not 1.875. So 3 by 16, I was sure that it is not 1.1875. So that means I have made some mistake. So this is the correct answer for this question. What it is? 0.9375 volt. Okay. So the next question over here is what? It is given basically in a dual slope integrating type digital voltmeter. For integration is carried out for 10 periods of the supply voltage 50 Hz. If the reference voltage used is 2 volt, the total conversion time for an input 1 volt is. Okay, fine. So we know what the formula is basically. So charging time into input voltage is equal to reference voltage into discharging time. Okay, into discharging time. So now if I want to calculate this charging time, it is always fixed. We know 2 to the power n tc into input voltage. So over here, if the reference is this, the total for an input is 1 volt. Reference is what? Reference is 2 volt. And discharge time, let this be T2 minus T1 as we have seen in the diagram. Okay, T2 minus T1, and this is T1. So over here it is how many bit in a dual slope digital time? Okay, the integration is carried out for, okay, so it is given in a dual slope integrating type digital voltmeter. For integration is carried out for 10 time periods. Okay, 10 time period, it's directly given. So we will not write 2 to the power n, it is given 10 Tc. So this is 10 into Tc is 1 by 50 is equal to 2 T2 minus T1, or this is the discharging time. So T2 minus T1, this is basically discharging time. So this comes out to be what? This comes out to be 10 by 100 or 0.1 second. Now, if you write 0.1 second, what do you think? Is your answer correct or wrong? So this is wrong. Why? Because here it is asked the total conversion time, not the discharging time. So if you look in the diagram, we have drawn it like this. So basically, this is your charging time, and this time is what? If this is T2, so this is T2 minus T1, which is your discharging time. Now basically they are asking this T2. So T2 will be equal to what? Charging time plus discharging time. So discharging time is 0.1. Charging time they have already given. It is what? It is 10 time period. So plus 10 by 50. So this is 0.2. So 0.1 plus 0.2 is equal to 0.3 second. So the answer for this question is 0.3 second. You have to be very careful while solving such questions, because you can see these questions are very basic question. But if you are not careful enough, you will make mistakes and you will lose your marks. Okay. So the next question, for this I will show you directly the shortcut trick. Okay, shortcut trick. It's very simple, or else it will be very tough. So look, an 8-bit unipolar. Okay, first let us solve it using normal method. An 8-bit unipolar successive approximation register type ADC is used to convert 3.5 volt to digital equivalent output. The reference voltage is 5 volt. The output of ADC at the end of third clock pulse. Okay. So here first let us calculate the step size. So step size is equal to full scale voltage, that is 5 volt, divided by number of step. So that will be 2 to the power 8 minus 1. So what we will get? So let me use calculator. So this is equal to 19.6 millivolt. Okay, 19.6 millivolt. So we have what? An 8-bit unipolar successive register type ADC. So initially at clock pulse 0, okay, at clock pulse 0, what is the value of your register and its corresponding analog voltage? Okay, analog voltage V0. So you can see at clock pulse 0, register is 000, okay, and corresponding output will be 0. At first clock pulse, the MSB bit will be 1. Okay. So for this, basically, this is what? This is 2 to the power 8. Okay, 2 to the power 8. That means 256. So this will be 256. Sorry, this is your 128, na? 2 to the power 8. Okay, so I have made mistake over here. This is basically number of steps, so that is 2 to the power 8 minus 1. So this is okay. So this is okay. This will be 128 into 19.6. So that comes out to be 2.5. 2.50 volt. Okay, so you can see basically what, that we have input as 3.5, so this is 2.5. So that means what, in the second clock pulse we will be adding one more 1 over here. Okay, so this is what? This is 128 plus 64. Okay, so what is the corresponding value for this? 128 plus 64, 19.6 millivolt. So this comes out to be 3.76. Now this value is more than 3.5. So in the third clock pulse, what will happen? This one, it will remain, but this one, it will convert to 0, and next it will becomes 1, 0, 0, 0, 0. So now let us check what is this. So this is 128 plus 32. We already have the answer. So this is the value of your register after third clock pulse, but I want to see what is the V naught we get. So this will be, so this comes out to be 3.136. Okay, 3.136. This is after third clock pulse. Let us see what happens at fourth clock pulse. Okay, at fourth clock pulse, what I am going to do, let this be 10110000. So this is what? This is your 128 plus 32 plus 16. Okay, so this comes out to be 3.44. So this comes out to be 3.44. So after fourth clock pulse, this will be the value. Okay, because it is 3.5. So this is okay. So at fifth clock pulse, what will happen? This will be 1011, and this will be also 1000. So look now, this will be 128 plus 32 plus 16 plus 8. So what is the corresponding value? So this value comes out to be 3.60. So this is coming out to be 3.60, which is greater than 3.5. That means at the sixth clock pulse, we will once again have what? 10110000. So that means 3.5 corresponds to this value only. Okay, 3.5 corresponds to this value, and this value has error how much? So you can see basically there is an error of 0.6, because this is your true value. True value is 3.5, and the actual value we are getting is 3.44. So there is an error of 0.6. So if they ask what is the error percentage over here, so you can do what? 0.06 divided by 3.5 into 100. Whatever percentage you get, you can write it as answer. Now this was actually what? This was little bit time consuming. We also have one very simple method. Let me show you that. So over here, our maximum voltage, first mark the maximum voltage and the minimum voltage. So maximum voltage is what? It is 5 volt. So this is, and this is 0 volt. So this is for 1111, and this is for 00000000. So now in between this we have 2.5. So 2.5 is for which binary value? So it will be obviously for 10000000, because in between 111111 and 0000 we have this value, and you can quite evidently see that this value has basically 2.5. Okay, fine. So now our input voltage is what? It is given as 3.5. So 3.5, it lies in which region? In this region or in this region? So this is between 2.5 and 0, and this is 5 and 2.5. So obviously it will lie in between this region. Okay. So now find the half of this. This is the half basically. So that is what? 5 plus 2.5, that is 7.5 by 2. So that is 3.75. So this is 3.75 volt. And this will correspond to which value? It will be 11000000. So now my value is 3.5. will it lie in this region or in this region? So obviously it is going to lie in this region. Okay, it is going to lie in this region. So in this region, if I take the half, okay, in this region I am taking the half. So this is basically 3.75 plus 2.5. So in this region it is basically 3.125. 3.125, and this region will be basically, if I want to write the binary, so this will be what? 1. See over here this was 1, but here it is 0, so this will be 0 1 0 0 0 0 0. Okay, now you see 3.5, it lies in which region? In this region or in this region? So you will say it lies in this region. Okay, it lies in this region. So you can see basically at the end of third clock pulse you are lying at this region, because why? You have 3.5 and 3.5 lies in this region. So you have already done 3 time iteration, because this was the first iteration, this is the second iteration, and this is the third iteration. So the approximate bit value, it will be this. Why? Because this is the third iteration, we got this value. So directly whatever you were getting after solving this much, you can get it like well in 2 seconds. Okay, so if you keep on iterating, so again you have to calculate the half value in between 3.75 and 3.125, you will get that. Okay, so you can do it, keep on continuously doing this and get the answer. So the next question, this is the last question. So the integrated output waveform for the dual slope ADC is shown in the figure. The time t for an 8-bit counter with 4 megahertz clock will be. So t is your charging time. So charging time, we know what? Charging time is 2 to the power n tc. So 2 to the power n means 2 to the power 8 into tc. So this is what? This is 256 into tc over here. It is what? So we have to find out. So this will be 4 megahertz. So that is 1 by 4 into 10 to the power 6. So this is 2 to the power 8 by 2 square into 1000 by 1000, because I can see millisecond. So this is actually equal, sorry. So this is actually, I'm very wrong. 1000 millisecond. Okay. So this is 2 to the power 6 by 1000, or 2 to the power 6 is 64 by 1000 millisecond, or this is equal to 0.064 millisecond. So which option? Option B is your correct answer for this question. Okay. So with this we cover our ADC and DAC. So if you guys have any doubt, what you can do, you can just message me on WhatsApp. I will be getting back to you if there is any issue anywhere. Okay. So hopefully you have understood this session. Okay. So see you in the next session. Thank you.